Stella? Yeah. Shall we start? Yeah. Okay. Very good. So great to see you. Thank you. Okay. So let's start the next session of the morning. Pleasure to introduce Iñaki García-Etxebarria, sorry. And he will be talking about deconfining a class of n equals to superconformal field theories. Please.
Thank you very much for the introduction. And thank you very much for organizing the workshop. It's really a pleasure to see everybody together again after such a long time. And thank you for inviting me to talk. So I want to describe some work that I've been doing for a while with Ben, so in these two papers, where we did the n equal to 1 case. But today I want to focus on some more recent paper from last summer with Ben, Ajit, and Matteo, where we apply these ideas to n equal to 2. And our goal here is to construct n equal to 1 Lagrangians for some n equal to 2 superconformal field theories. And the theories that we'll discuss are classes theories. So we have all seen this, that you can construct some interesting four-dimensional theories by taking the 2,0 theories in 6D and putting in Riemann surfaces with punctures. And we know a lot about these theories. These classes construction is very powerful, but for most of them, we don't know Lagrangians. So it's fair to say, I think, the situation right now is that we know many more theories than Lagrangians. We have geometric constructions, but we don't have a Lagrangian. But if you have a Lagrangian, then you can check the things you know from different methods, and typically you can say more powerful statements. So Lagrangians are still useful, even if we like them very often. So what we wanted to do, and for this we use brain techniques and geometry, is to first we constructed some brain system that engineered the superconformal field theory, and then as you will see, we define two operations. We call them deconfinement and deformation, that, or brain bending sometimes, that allow us to systematically, for all the class of theories that we cover, engineer Lagrangians for them. So I will have to use two different ideas for duality. So we call duality many things in physics. In this talk, I will use two notions that we call duality. The first one is what I will try to refer to as Monton and Olive duality, or sometimes S duality or SL2C duality. And when I talk about this kind of duality, what we have is a conformal manifold of theories. So here I'm drawing the case of n equal to 4, for example, where you have some parameter tau. Tau lives in the upper half plane, so here I have conformally mapped the upper half plane to disk. And now by changing the value of tau, you change the theory that you're discussing. Right? So you're basically moving in this conformal manifold. And as you move to points at the boundary of this disk, you're going to different wiggly coupled regions in different duality frames. So from this kind of point of view, the typical statement of S duality, you start with a wiggly coupled equal to 4 theory, you take the coupling to infinity and you hit another wiggly coupled description, will be something like starting here and going to here, or maybe here to here. Right? But when I talk about S duality, what I have in mind is I have a plane like this, and I'm playing with moving around this manifold in different ways. And seeing what happens when you hit the edges. So for me, this will actually be a tool. I will use this S duality as a tool for doing what I really want to do, which is engineer n equal to 1 theories in the same universality class as some n equal to 2 theories. So in an equal to 1 context, typically we refer to universality as cyber duality. We have two theories which are different in the UV, and they flow to the same fixed point in the IR. Of course, these two concepts are related in some cases, but they're generically different. So what I want to do is, what I want to obtain is a statement about universality. So I want to engineer some brain construction that has n equal to 1, and then it will not be conformal, it will flow. And I want to engineer this system in such a way that it flows to some interesting n equal to 2 superconformal field theory. And as I said, this first concept of duality will play a role in allowing me to engineer this thing systematically. Yeah? Is the distinction clear? It's really a statement about the Lagrangian lives here, and as it flows, it will hit some interesting n equal to 2 theory. Okay, so the ones I want to discuss today, they were the simplest cases in which we could apply our ideas, are superconformal field theories that appear in the following way. They can be described in a simple way. You start with the SU2n theory, n equal to 2, with a hyper in the symmetric representation and a hyper in the antisymmetric representation. In this case, you compute the beta function. You see that this theory has a marginal deformation given by the complex coupling of SU2n. And you can start moving the parameter space of this complex coupling in this little disk I was drawing before. So if you start from weak coupling, well, this is the description that's good of the theory, but you can start cranking up the coupling, the cage coupling, and go to a strong coupling. And at the strong coupling, you find something that well, people have given it a name, although we don't know a lot about it. So you find a theory that can be described in the following way. There's some theory known as R2 to n minus 1. The n and n here is the same. So this is some strongly coupled CFT, an isolated CFT. It has a global symmetry group, which is a spin for n plus 2 times U1. Well, this is the covering form of the symmetry group. And well, this is a flavor group. So what you do is you gauge a subgroup of this flavor group. So for me, this curly arrow means gauge this subgroup of the flavor symmetry group. Okay, so this by itself is some superconformal field theory, and I'm gauging part of the flavor symmetry to obtain another theory. And this statement is that at the strong coupling, this theory should be described in this way, with this factor weakly gauged. Right? So my goal is really to give a Lagrangian description for this theory here. The same techniques allow you to do something related, which is you start with SU2n plus 1. So before it was SU2n, now it's SU2n plus 1. And you get something similar. There's another theory that people have called R2 to n. It's similar in its construction, although the properties are fairly different. The global symmetry now is USP times U1, and you gauge USP2n subgroup. Okay. So originally not much was known about these theories. You can construct them in the class's description. You start with 3 punctures. One of them is minimal, and 2 of them are full punctures, and the full punctures are twisted. These are technical terms. They won't matter too much in this talk. But if you know this data, you can construct things like the central charges, the Coulomb and Higgs branch dimensions, and the indices of the theory. Okay, so this might seem like a random choice, but in fact, these are interesting theories. So the R2-3 theory is the same theory as the Minahan-Michansky E6 theory at level 1, or it's also the T3 theory. So this is one of the fundamental blocks in this class's business. Sort of the simplest or one of the most important strongly coupled CFTs that you can construct in equal to 2. So with our techniques, we can give Lagrangians for this one. Another one is another interesting theory at rank 1, R2-2. This is sometimes known as the Argyres-Wittig theory with global symmetry USP4 times U1. It's perhaps less famous, but also quite an interesting theory. So these are my goals. As it happens, this one, which is perhaps a little bit harder to study in class's description, will be a bit easier to study with our methods. And this one we can also understand, but it will be a little bit more complicated. Okay. So as I mentioned, I want to construct n equal to 1 Lagrangians that flow to these superconformal field theories. And these are theories in the same universality class. And we are not the first ones to attempt such a thing. So already 7 years ago, Gade, Razamata, and Villette, they proposed a bit exotic n equal to 1 Lagrangian. And it's a bit exotic, even if it's really useful. But it's a bit exotic because what they do is they start with an n equal to 1 theory that takes some coupling to infinity in the superpotential. And they argue that when this coupling is infinity, you get an extra symmetry that they gauge. So it's not entirely Lagrangian in that sense. You have to go to a point that you don't control. Still, you can read things like the superconformal index from this computation. Another famous paper, a series of papers, was the ones that started with Mariyoshi and Song, where they provide an equal to 1 Lagrangians for many Argyres-Douglas theories. So the theories that I will construct are not Argyres-Douglas theories. The R2K are different. But in some cases, you can connect them. So later on in the talk, if I have time, I will explain how, with the Lagrangians that we find for R2K, you introduce some deformations that will flow to some Argyres-Douglas theories. And when we do this, we reproduce the Mariyoshi-Song Lagrangians. And in a paper that's amazing, Gabi Safrir proposed n equal to 1 Lagrangians for R2 to K plus 1. And they just look different. I don't know how to relate the two results. Gabi basically, he obtained the result from bottom up. He knows a lot about the theory, and he was able to construct an equal to one theory that had the right properties. And ours is more top down. So we were looking at the geometry, and we were kind of guided by what the brains were doing. And the answer looks a little bit different, but they both seem to be consistent. So maybe this is a case in which we have two cyber-dual and equal to one theories. We haven't been able to relate them. Okay, so what's the strategy? So these are two K-theories, as I mentioned. They appear in the strong coupling limit of SUN with symmetric and antisymmetric. And constructing this system in 4 dimensions is quite easy with brains. So one realization that we will use is that you can start with n D3 brains, which are probing an orientifolded or bifold singularity. So this goes back to the 90s. I'll describe the precise prescription later. But let me ignore that for a second. There's some geometry in which you can put brains and orientifold, and you obtain this gauge theory. But what do we do? Okay, so in terms of toric language, which I will review briefly later, this geometry here, C2 mod Z2 times C, can be described as this toric geometry here. The orientifold, in my notation, something I developed with Ben, we show that can always be encoded into some refinement of the lattice, some quadratic refinement, no, quadratic, order 2 refinement of the lattice. So this little star tells us which kind of orbifold, so which kind of orientifold we have. Right? So this is just this thing here, the orientifold of C2 mod Z2. And now here comes what we really do. What we would really like to do is take this configuration to a strong coupling. But for technical reasons that I'll try to explain in the talk, what we do is a little bit more involved. So we take this geometry, we attach another piece of an orbifold to obtain a geometry like this. This geometry, which is more complicated, this is the one that we actually S-dualize, using ideas that we developed in these papers. And since we know this as the strong coupling, we can resolve and obtain the answer here. So the step in which I mentioned that we use S-duality as a tool is essentially this one here. Okay. So let me try to describe how to do S-duality for n equal to 1 theories. And for that, I will start by describing how to do S-duality for n equal to 4 theories, which is the more familiar case. So you have a 4D n equal to 4 theory with gauge group G and gauge coupling tau. And as opposed to last talk by Sakura, I will essentially ignore everything having to do with global structure here and higher form symmetries and so on. You can refine this discussion, but it's hard enough if you ignore that already. So there's a complete equivalent description with gauge group the Langlands dual, G check, and coupling -1 over tau. So for example, if you put theta equal to 0, you're saying that the theory with gauge group G and coupling G, small g, is the same as the Langlands dual gauge coupling, so a gauge group, and 1 over G. So here are examples. For U1, you get U1 again. For UN, you get UN again. But as UN, you get some other theory, which is locally similar, but has different global form. For SO2N, the same thing. The case that's perhaps more interesting or more in your face is the SO2N plus 1, which if you take the Langlands dual, you take the strong coupling limit, you get SP2N. So here the two theories are locally different. They look very different even for a perturbative observer. So this is a very non-perturbative duality and exchanges electrically charged operators with magnetically charged ones. It's hard to prove. But you can understand it in string theory by the following construction, which was due to Witten. So he made the following argument. Start by constructing the n equal to 4 theory in terms of brains. So one convenient way of doing this for this kind of argument is by putting D3 brains in flat space. Then the gauge coupling on the D3 brain, this G Jamils, or G4D, is simply the square root of the string coupling. So in pictures, you have some 4-dimensional theory that lives on some sort of defect, here D3, and has a transversal space, which in this case is simply R6, which I will want to understand as a cone over S5. So I want to do this more generally because I want to do n equal to 1 later. So instead of saying S5, I say L5D. Okay, so The low energy theory is fully determined by the supergravity solution up to the higher form data that Sakura was talking about. So one can determine robust results without knowing much of the dynamical details on the duality. So instead of thinking of the field theory itself, which is a hard problem to solve, what we think is what happens at infinity, which is supergravity, and supergravity we think we understand what it does as you go to a strong coupling. We know how to dualize type 2b. It just becomes type 2b supergravity. If you go far enough from the singularity, everything is weakly carved, so we think we understand the physics. And then once you have done this, you look at what happens at infinity, now you try to reconstruct what's going on at the dual defect. Okay, so here's what you would like to know. What happens in the 4D field theory, but this is hard as you go to strong coupling. Instead, you embed this in string theory, you look at what happens at infinity. I put this easy, this is perhaps an overstatement, but this is doable. And then you try to reconstruct what happens once you have these dual supergravity fields, which kind of brain configuration in the dual could give you rise to these supergravity fields. Okay, so this is the problem I answered with pen. So in the case of n equal to 4, well, we can argue that the charges of an O3 plane are classified by the cohomology on the space that surrounds the origin. So you have an O3 plane in flat space. The geometry that is surrounding the O3 plane is S5 modded out by the set 2, which is the involution of the O3 plane. So it's identifying opposite points in the S5. So total geometry is S5 mod set 2, or RP5. And now you want to classify the supergravity fluxes living in there. So you have to distinguish between those fluxes that feel the -1 FL omega action of the orientifold and ones that don't. So F5, for example, doesn't feel the -1 FL omega. It maps to itself under that part of the action. It only feels the geometric action of the orientifold. So these F5 fluxes live in ordinary cohomology. So cohomology of degree, in this case, 5, with coefficients in Z. So you go and compute the cohomology with degree 5, coefficients in Z, it's like this, of RP5. So we know that we have discrete F5 fluxes around the O3. And that's something that's not surprising. It's telling you that there's a flux at infinity that's counting how many D3s you put on top of the O3 plane. And you can put as many as you want, so this is set valued. The ones that are more subtle are the ones that feel the action of the orientifold. This -1 FL omega sends B2 and C2 to -B2 minus C2. So these fluxes, H3 and F3, they don't live in this cohomology group. They live in a different cohomology group, which is known as the cohomology group with local coefficients. This is a version of cohomology that takes into account this extra action that when you invert the space-time point, you map to the image, you also flip the sign of the fields that you're computing the cohomology for. Keeps track of this extra sign. And if you compute this thing, you find that at degree 3, where these guys live, there's actually set 2. Notice that there's no set 2 here, but there's set 2 here. So the O3 planes, they not only have the F5 flux at infinity, but they have an extra choice of a plus or minus for H3 and an extra choice of plus or minus for F3. So O3 planes come in 4 variants, essentially, 2 times 2. So you can draw this a bit more visually here. You can draw the value of the Ramon-Ramon flux. This F3 is set to valued, so it can be 0 or 1. And this Neversort-Neversart flux, it can be also 0 or 1. And then what we did, he looked at this and said, okay, I can identify these things, right? So the one that lives here in the O3 minus, that's going to be the SO2N. This is an SL2C singlet. And that's fine, it's compatible with what's happening at infinity. So SL2C, if, for example, you do the S element, the duality element, the S duality element of SL2C, you exchange Neversort and Ramon fluxes. So you're sort of flipping this diagram across this diagonal. Right? This gets inverted. So this statement, this means that, for example, the thing that lives here, which is SO2n plus 1, gets exchanged with USP2n, which is the standard statement of n equal to 4. And this one is in singlet, because if you look at the other transformation in SL2C, the shift of the action, these two stay invariant under a shift of the action, but these two get exchanged. So there's an SL2C triplet, which is these 3 guys. They're really the same theory. And there's a singlet, which is the SO2n theory. Okay. So this is the idea. Here we're really looking at the fluxes at infinity. But in the n equal to 4 case, Witten could identify what was going on at the singular point. He said, yeah, this point must be SO2n, this point must be SO2n plus 1, and so on. And in this way, you reconstruct the action of duality. Even if you didn't know what n equal to 4 duality is, you could read it from this action on the fluxes at infinity. So we follow the same philosophy in n equal to 1. There's no particularly n equal to 4 aspect to the question. You can do the same thing in equal to 1. So in the papers with Ben, what we did was the same thing. We constructed some interesting theories n equal to 1 in the same way. There will be D3s on top of orientifolds with some transverse cone, and the base of the cone will be some space, some 5-dimensional space. We figured out which charges in supergravity characterize the configuration. Now, because we're in supergravity, we know what happens to these charges in the dual frame. And then we were able to reconstruct which kind of brane configuration here gave rise to these charges. And this way, we can identify what S-duality does in these n equal to 1 theories. I emphasize the picture here is the same as n equal to 4. You have a marginal coupling, and we are moving the space of CFTs, but in this case, n equal to 1 CFTs. OK, so in these papers with Ben, we solved it. I'm not going to tell you the reasoning for lack of time, because I want to do n equal to 2. But we did this for large class of n equal to 1 superconformal field theories. And the ones that we were able to do systematically are the ones that arise from D3 branes probing orientifolds of singularities. But we simplify the problem a little bit. First of all, we assume that the geometry is toric before and after orientifolding. And the reason for that is that whenever you have a toric singularity, you have some very nice general techniques, combinatorial techniques, both on the geometry side and on the field theory side. So in field theory, you can use the brane tiling formalism that was developed by these authors. So this is a way, using toric geometry, of obtaining large classes of results. It's not particularly meaningful physically, but it's useful in the context of systematizing what you're doing. We also assume that the singularity is isolated. So there's a singular point in your space, and everything else is smooth. And that's because we wanted to deal with a smooth geometry of the horizon. Now, again, this is not particularly deep. It's just something that made our life easier. Something that's perhaps meaningful physically is that we also assume that the orientifold locus is isolated at the singularity. So there's no component of the orientifold that goes to infinity. Right? And the reason for that is that S-dualizing in this case, it would be an O7 plane that goes to infinity is a little bit tricky. S-dualizing O7 pluses, for example, is not very obvious. Yes? Yes. Yeah, exactly, because we're in type 2b, and S-duality doesn't act on the geometry. So the geometry. Thank you. So yeah, let me do a sort of lightning review of toric geometry. So toric Caraballo n-folds can be described by n equal to 1 convex polytope, the toric diagram. And here are examples of toric diagrams. So you have one for C3. So this is n equal to 4 cases. But you can complicate things as you like. So the conifold, orbifolds, and a bit sloppily, I'll be calling this DP0 and DP1. Strictly speaking, these are Caraballo cones over. OK, so you need to know the same information. So what's the fluxes that you can turn on infinity in these geometries? And, well, you can do that. With these restrictions that I mentioned before, you can give a general answer. So for a toric orientifold of a toric cone, which has k sides, so we have 1, 2, 3, 4 sides, k equal to 4, the isolated singularity at the origin, so the geometry is singular only at the origin, doesn't go to infinity, and the orientifold is fixed at the origin, then we could show that the cohomology with twisted coefficients, the thing that measures where H3 and F3 lives in this group. K minus 2 copies of set 2. So let's go back for a second. K, remember, is the number of sides. So if you go to flat space, then equal to 4 Ks, you have 3 sides. 3 minus 2 is 1. So you get that H3, where the fluxes live, is set 2, which is the thing that I mentioned before. But now you give the general answer for any toric variety. It's very simple. I just count number of sites and subtract 2. For example, the first example that's sort of qualitatively different from flat space is DP1. So this is the real caveat over Y21. And you can compute where the fluxes live on the boundary. So here the boundary is this Y21, but quotiented by Z2 because you have an orientifold, quotient in the geometry. And you want to put local coefficients. But here's the general formula. Because you have 4 sides, 1, 2, 3, 4. This is precisely this geometry here. You get Z2 plus Z2. Okay? Remember, this is where H3 lives. There's another Z2 plus Z2 where F3 lives. So in total, you get 4 possibilities here, times 4 possibilities for the Ramon-Ramon sector. So in total, you get 16 orientifold types for DP1. And now you can go and arrange these different fluxes in duality orbits, because we are doing supergravity, this is easy to do. And here they are. So Ramon-Ramon, Nevesource-Neveschwarz. And the duality orbits are, this one is a singlet, these 3 are a triplet. So S duality is reflection along this diagonal. And this shift of the action, tau goes to tau plus 1, are these horizontal arrows here. So, for example, tau goes to tau plus 1 doesn't do anything here, but it exchanges these 2 and exchanges these 2. Okay, so now you can just stare at this for a second and realize the duality orbits. So you get the singlet, a triplet, and a triplet. And interestingly, you also get a sextet of SL2C. These 6 theories are related by SL2C transformations. Okay, so that means that you have something of the order of 10 different weakly coupled limits. We go from 16 to 10 because tau going to tau plus 1, you don't see that perturbatively. So I'm sort of referring to it as the same theory. Okay. So we have to identify these theories. We have to map for each dot here in the same way that Witten did and said, this is SO2n, this is SO2n plus 1. Now we have to give theories living at these dots. That's our task. If we are going to solve an equal to 1 S duality. Okay, so let's do that. Because we're in the toric context, we have very powerful systematic techniques that were developed by a number of authors. I'm being a little bit unfair here, but when I tried to do proper referencing, it was taking the whole slide. I couldn't really do it. But this goes back to early work by Harani and Witten and other authors. And there was a lot of building up. But sort of in these papers, around 2005, this work coalesced into a very systematic picture, the Denver models. So I'm going to brain tilings, I'll review that. So say that we have this DP1 theory. We have the toric diagram here. So how do you construct the field theory that lives in here? Okay, I have one of these stars that's telling me what the type of orientifold. You can ignore this. It's my paper with one. But the important thing for doing the field theory is doing the following algorithm, if you like. First, you draw these perpendicular legs. They're perpendicular to each side of the toric diagram. Okay, so you do that. Now draw a torus. So this is a torus. These 2 sides are identified, and these 2 sides are identified. And you draw a line on the torus that goes in the same direction as the leg that you're putting. So I have a vertical leg here. The red one is the red line here. The blue one here. Green and black. Right? The slope is the same. Now, in general, this is how you obtain the brain tiling with an extra rule I'll mention in a second. There's an extra subtlety here, an extra step, that because we have an orientifold, there will be 4 fixed points on the torus. So basically, you obtain this by T-dualizing twice this geometry. There will be 4 fixed points in the torus. You can argue this. And each of these lines must pass through 2 of these fixed points. Okay, so these are the rules of the game. Same slope, and it has to pass through 2 points. Okay, so you obtain a diagram like this. But I have colored it in different ways. So what do the colors mean? Well, there are some, as you look at the little triangles that have been created by drawing these lines, there are some colors, some triangles that you have paths going anti-clockwise and clockwise. Those give rise to superpotential couplings. I'm giving you a recipe here, but this cannot be justified, okay? Just so you can read these diagrams. And there are parts where you don't have such a thing. Then you have these white areas. The white areas are gauge factors. So you have an SU per white area here, some superpotential couplings, and some bifundamental fields that come from these places where 2 SU factors touch. Okay? So in this way, you can read the gauge group, the matter. So gauge group are the white areas. The matter, which are these intersections here. They live here, and here, and here, and so on. And the superpotential couplings, which are these shaded areas. So all the information is given to you if you follow this algorithm. All right. Now, there was one thing that you might be wondering. I mentioned that each one of these has to have the fixed slope, and it has to pass through 2 of these. You can argue this systematically. I just gave you the prescription. But if you actually think about it for a second, there's 2 ways of doing this. There's 2 solutions of this problem. One is this one here that gives you a standard answer. And there's another one here in which you have 4 of these lines passing through an orientifold point. And here's where the magic happens in a way. Okay, I have to explain what this is. So whenever you have 2 of these intersecting, you get a hypermultiplet. We understand how to do this Lagrangian. Whenever you have 4, that's the bit that we needed to understand with Ben to solve this problem. Okay. So as I mentioned, we want to map fluxes to geometry, to field theory. And in this paper, we gave a prescription for if you give me the flux, we tell you through which fixed points do these lines pass. The answer is not very difficult to state, but it's also not very interesting for this talk. I just want to know that now we know how to do this. You give me flux, I give you a picture like this. Okay? So we can map duality orbits to themselves easily. Okay, so more interesting is what happens whenever you get something like this, maybe 4 NS5 branes intersecting, something non-Lagrangian. What do we do with it? So we give an answer. Before I answer that one, let me answer one which is slightly easier to understand. So imagine that you have 2 branes like this, two legs like this, one going like this and one going like this. That's in fact one of the cases that are interesting for us in equal to 2. So if you follow this prescription in the torus, you will have, say, a line going this way and another line going just on top in the opposite direction. So 2 lines on top. So in order to understand this configuration 2 NS5s on top of each other, what you can do is bend them a little bit, open them up a little bit like this. We call this brane bending. And now you get a gauge factor here and some bifundamentals and some superpotential couplings. So this one is easy to solve. You just bend the branes and you obtain some Lagrangian. So this is not very complicated. The one that's more difficult to understand is what happens when you have 4 or more NS5 branes intersecting on top of an O5 plane. So this is the simplest case in which you get something that the answer was not known before. Well, when you have 2 of them intersecting, as I mentioned before, you get a free chiral multiplet. When you have 2 or more, so this is 2k, so when k is bigger than 1, we claim that what you get is an interacting, isolated, n equal to 1 superconformal field theory, some sort of conformal matter, n equal to 1, which we call the TOK theory. Or for k equal to 2, we call it the quad CFT. In this case, we were able to give Lagrangians for any k through something that we call deconfinement. So what's that? So let's think about the k equal to 1 case. That's the case in which you have just 2 branes intersecting and you get a symmetric or antisymmetric. So in the case of the antisymmetric, many years ago, Bercos and Pouliot, they constructed Lagrangians, sort of complicated Lagrangians, that if you let them flow to the IR, they give you a single antisymmetric. Oops. So Interrogator and Pouliot observed the following. If you take USP n-4 with n chiral multiplets in the fundamental, you let it flow, it will confine, and then you end up with a meson with some superpotential. It's almost the antisymmetric, so this is an antisymmetric of the flavor group, but it has an effective superpotential. You can fix it. You can remove the superpotential by complicating the original theory slightly. So instead of putting USP n-4, you add some extra flavors here, you add some superpotential for the flavors, and the net effect of adding all this extra baggage is that when this theory confines to the AR, it gives you a single antisymmetric field. Right? So this is a very complicated way of describing a free field. So why is this useful? Let's think about what this does in terms of the brane setting. So in the branes, we have an orientifold and 2 NS5s. And because you have the orientifold, these two, the bifundamental gets projected to the symmetric or antisymmetric. So I'm claiming that this antisymmetric, say, can be understood also as the IR description of this complicated gauge theory. So how does this complicated gauge theory appear in the string picture? Well, what you can do is you have this orientifold here, and you cannot really move the branes away from the orientifold, because the orientifold maps the brain to itself. You cannot deform them away from the branes. But what you can do is kind of take this thing and open it up. Open a little bubble here. And of course, by charge conservation, this brain cannot end here, so it kind of goes on top of the orientifold by plugging this bit in there. Okay, so this is a more complicated, non-supersymmetric brain configuration. But if you now look at what the effective description of this brain system is, forgetting about supersymmetry for a second, is precisely this quiver here. So this field theory description that was found in the 90s, you can understand equivalently in the brain system as this opening up a bubble around the orientifold, taking the brains away from the orientifold by opening up and adding this little bubble on top. Okay, and now this is useful, because for 2 brains, for 2 NS5s, we know what to do. But whenever you have 4, where we didn't know the description, we can do this. We can take 2 of them, say red and green, and pull them apart through this method with the extra bubble on top. And now we have a complicated brain system, but it's not too complicated. Every intersection is between 2 NS5s. So we can read the Lagrangian. We can open these bubbles everywhere, no matter how complicated the system of NS5s we have. You have 6, you deconfine twice. Okay. So in this way, we can provide Lagrangians by opening up these bubbles for all of these theories that appear in the other duality frames for the n=1 theories. Okay, so in summary, I'm skipping a lot of details and just showing you pictures, but everything is spelled in a lot of detail in the paper. In order to construct Lagrangians in n=1, in these strongly coupled phases, we introduce 2 operations that we conjecture are irrelevant deformations of the CFT that give you Lagrangian description. One of them is brain bending. You have 2 parallel brains, and sometimes you can just bend them, and they're not parallel anymore. That's the easy case. The other one is the confinement, this opening up of bubbles, which is a bit more subtle, but something we can do. In this case, you obtain Lagrangians for all duality frames. Okay, so let me do the example, come back to the example of DP1. If you try to do the orientifolds of DP1, there were 2 phases that were known before through this paper. And they are these ones. You get a Lagrangian with SUN, and symmetrics, antisymmetrics, some superpotential. You can read it with these techniques. It's basically reading what appears in here. Okay, somewhere. Probably not a good idea. Okay. Sorry. Here. This one. You look at the field theory, you will read with the rules I mentioned from here. And it's the one I wrote later. Okay. There we are. So these are the classical ones, but you also have 2 new phases which involve these strongly coupled sectors, which, because these are, you should think of them as matter, some sort of strange matter, but these are isolated CFTs with some global symmetries. You should think of them really as some sort of matter. So we draw these little diamonds that mean that one of these conformal matter lives here. But importantly, we know Lagrangians for all of this. Okay? So every time I draw a picture like this, even if the right way of thinking in some sense is in terms of an isolated CFT, I can always write an n=1 Lagrangian. Okay. So DP1 was a little bit complicated, and I should mention that in many of these cases, the S-dual of this might be something like this. Right? So this was important for understanding the full n=1 duality picture. In other cases, it's just unavoidable. If you do DP2, for example, the next more complicated case, every duality phase includes TO2. So if you try to write any orientifold of DP2, you will need some of these sectors. But again, now we understand. Okay, so let's do n=2. Yeah, perfect, thank you. So as I mentioned before, we're interested in understanding the strongly coupled limit of SUN with symmetric and antisymmetric. And this is D3s probing an orientifold of C2 mod Z2. So this is the toric diagram for the geometry. It has legs like this, 2 like this, and 2 parallel. So because I have these 2 parallel ones, this complicates the story a bit, meaning that there's a singularity that goes to infinity and intersects my boundary at infinity. So I have to worry about fluxes in singular spaces. I don't think this is a very deep problem, but to make our life simpler, some way, what we did was, okay, take a copy of this and reflect it and put another copy like this, glue these two geometries. And now you no longer have any singularity at infinity, all the singularities at the origin, so we can apply our techniques straight away. So this thing I just described, we can do. And then you can sort of remove all the extra scaffolding that you introduced. You do a partial resolution, but you have a Lagrangian. Doing a partial resolution is no big deal. So that's what we did. Okay, so for F0, how do things look? You have three phases. One of them, like this one, that has this conformal matter here, these four branes intersecting. In fact, it's a little bit perverse because it has both these four branes intersecting and parallel branes. So first you have to bend, and you still have this quad CFT. Okay, but you do it. And it has another one, which is here, that has one of these sectors, which is more standard, and then some bending. And then the purely Lagrangian one, which is this one. Okay, so we obtain the theory that we want by starting with this one and Higgsin. And in this way, because I know what the strongly coupled answer is, I obtain Lagrangians for R2n minus 1. So in particular, if n is odd, when I go to strong coupling, I land here. If n is even, I land here. But we know how to construct Lagrangians for this. Okay, so here's this beauty. This is the Lagrangian for E6 Minahan-Nemetshansky, or if you want the T3 theory. It's not very transparent. But I emphasize that we never guessed this. We read this from a picture, right? We have these rules that you just follow them. There's no ambiguity. You get this Lagrangian. And checks that you can do. Both the A and C are as they should. The superconformal index is what it should be. The Higgs and Coulomb branches have the expected structure to the degree that we check them. And the mass deformations land where they should. But I want to present maybe in the little 1 minute or so that I have, one picture that's perhaps more transparent of what these theories are, really. So you can sort of unpack these operations that we are doing a little bit and reformulate them in a more abstract way, which I like more. You start with these quad CFTs, this strongly coupled matter, and what you are doing is, well, these theories have mesons, so flip one of the mesons, and have global symmetry, so gauge part of the global symmetry. And the claim is that if you do this, for this conformal matter theory that I remind you has a Lagrangian, so we understand all of this in terms of Lagrangian language, is what I wrote before. This theory lands on n equal to 2 E6 Minahan-Nemetshansky. Okay, so this is n equal to 1 father of Minahan-Nemetshansky. Okay, we could do R22, which was a bit more mysterious before. It turns out to be simpler in this language because it doesn't involve these strongly coupled sectors, just brane bending. So it's nice. And Mariusz song, very quickly. Sorry. Yeah, Mariusz song. So if you start with the R22 theory, there was a proposal by Beam and Pelaers that if you start with R22 and you do a partial closing of punctures, meaning a Higgsin, you end up in one of their Years-Douglas theories. So if you take the Lagrangian that we give for this theory and you do the Higgsin that they suggest, we indeed end up reproducing the Mariusz song Lagrangian. So that's a nice check. Okay, so what do? We start by embedding things into toric geometry, attach singularities so we end up with n equal to 1, go to strong coupling, know what happens at the strong coupling. This is an trivial step, of course. But nicely in n equal to 1, we know what to do always. We can always construct Lagrangians. So this is very general. And then we just remove the extra structure that introduces for convenience. So in our paper, in this latest paper, with Matteo and Ajit and Ben, we did only the simplest one. It's already very rich. It gives us the R2K theories. I'm sure there are many other things we could do. But the thing I think is more important, perhaps, is that we did all this because we had the technology ready to go, the n equal to 1 story. But these operations seem to be a bit more intrinsic. This deconfinement and brane bending seem to be operations that you do in the brane system without really having to be n equal to 1. So I really wonder, I think it will be very interesting to understand an equal to 2 avatar of these operations. And with this, I finish. Thank you.
Thank you very much. Oops. Are there any questions, comments? Yes, please.
In the random picture you had, it looked like a
Yeah. Yeah, great. So whenever you have choices like that, there are cyber dualities. Cyber dualities. There are standard cyber dualities. Yeah.
Any other questions? Yes, Jonathan.
So you didn't mention like flat or anything like that. Is there a way to include the fact that it's in the object and story?
Yeah, there's a bit of that in the paper. Yeah, there's some cases in which you have interesting results. Like I started with SU2N with symmetric, antisymmetric. Those are all anality 2 representations, so it's a set 2. And you might wonder about the choice of global structure and how they agree between the two sides. So we did that in the paper. That matches. There's probably more to be said, but we did it a bit.
All right. Thank you very much.
Thank you.
And continue with the next speaker. I think you can switch microphone.
Yeah, but it's cut.